Hello students, welcome to your own YouTube channel where we are learning the concept of physics, chemistry and mathematics. And today we have to learn about the topic and it is capacitor. So students, you also have been seeing the electrical equipment just look like this, and the equipment that is held between my palms, it is known as capacitor. First I have to disappear this capacitor, then we will learn about the concept related to this. So students, we have to define the term capacitance. What is capacitance? Capacitance, it is defined as the capacity to store or collect the charges on the plate of a capacitor is called the capacitance of a capacitor, and we measure the capacitance of a capacitor in farads. You can note down the definition of capacitance as I start to write it on the whiteboard. So students, we have capacitance. As from the definition, it is clear the work of a capacitor is to store the charges. That means capacitor stores the charges, and that charges will be stored in their plates. So we also can define the capacitor as the electrical equipment that is used to store the charges on its plates, is called a capacitor. Before starting the formula derivation of a capacitor and some points related to the capacitance, I want to make you learn about the electric field, as we have already studied about that point. An electric field for a rectangular plate can be determined from the Gauss theorem. From Gauss theorem, we have the relation total electric flux is equal to the reciprocal of epsilon naught, that is q times. So we can see we can say flux is the q times reciprocal to the permittivity of free space, that is epsilon naught. Again, we also have the formula for a flux, and we know it in the term of E dot A. Flux is a scalar quantity, so we have a dot product of electric field vector and area vector. We can also rewrite it for the magnitude of this as E multiplied by A, that is normal area, and the angle between the electric field and normal to the area, that is cos theta. For the Gauss theorem, we have to redesign the surrounding surface for this plate and the charges inside the plate, that is Q, and here we have the surrounding surface in all over direction and electric field lines that is traveling from positive to negative charges, or it will generate from a point positive charge. If we have taken a positive charge inside this closed surface, that is Q, total electric field lines will be generated in such here we see that for this point, if the plate is in such a way in this direction, and here we have x axis, for vertical line we have y axis, and that is direction that is close to you, it is z axis. Again, for vertical line, for the y axis, our electric field lines that is traveling to this direction and normal to the area is also for this direction, it will be angle to 0 degree. Again, we are looking for this side, electric field lines are traveling towards to me, and the area vector also towards to me, and the angle between electric field and area vector is 0 degree. So it is countable. But for the vertical line, for the y axis, electric field lines and area vector direction is just perpendicular for each other. Then the angle is equal to the cos 90 degree, and cos 90 degree will make it as 0. E multiplied by A cos 90, that will be 0. So the electric flux will not be countable for the y axis, it is only countable for x axis, and we have to find the electric field. Then we have formula Q by A epsilon naught. Here the angle is 0 degree, so it is replaced by 1, and our formula is for electric field E equal to Q by A epsilon naught. Again, if we find the electric field at a particular direction, this electric field is for the total flux that is generated surrounding the surface. But if we have to find the electric field for this plate at this point, then the electric flux that is coming to me is not countable. The electric fields that are going far away from me in x axis, it will be countable. So we see here half of the flux is not countable. Then we have half flux is used to count at this direction when we have to find the electric field. Again, so if we have half flux used, it will be denoted as Q by 2 A epsilon naught for at any point for this plate if we have to find electric field at this point P. And the electric field lines just opposite to this direction will not be counted because we have to find the electric field at this point. So we cannot consider it. Again, I am discussing about the capacitor that is in the shape of a sphere. If we have a capacitor in such a way and it is in the form of a sphere and the charge that is held on its center is positive charge, that is Q, and it is a metallic surface. If Q charge is inside here, then there will be an induced and opposite charge that will be equal in magnitude, and it will be minus of Q charge and it will be negatively charged. But the magnitude of both charges are same because here we have induced the charges. Here the capacitance of a spherical capacitor will be 4 pi epsilon naught r. Here r is the radius of that sphere. So we see here from this formula C is directly proportional to the radius. If we increase the radius, it will increase the surface area of this sphere, and then the collectivity of charges on its plates will be increased for the increasement in the surface area of this sphere. Again, we are denoting the point. We are denoting the point C is capacitance of spherical capacitor. C is directly proportional to the radius of this capacitor. This type of capacitor is useless because the capacitance of such type of capacitor is very low and it is no more useful because we have to increase the capacitance. We have to surely increase the radius. For this reason, we use the parallel plate capacitor, and it is in the form of a cylinder because for a cylinder we can find the maximum surface area for the parallel plates. Now I am discussing about the parallel plate capacitor and its structure. A parallel plate capacitor is in the form of two plates that are parallel to each other, and area of the plates are same for both plates, and it is A. Area of these plates is denoted by A, and it is both for these plates, and the distance that is separated for these plates is denoted by D. If we connect it to the source of EMF, due to the source of EMF we have the potential difference between two ends. Here we have two ends, that is V. We have potential difference in such a way. We have connected this plate with the positive side of a cell or a battery, and second one plate is connected to the negative side of or negative terminal of cell or EMF. So there will be charge that is connected to this plate is positive in nature because it is connected through positive terminal, and again it is connected to the negative terminal, then there will be negative charge on these plates, and the amount of collecting charge will be same for both plates. Again, just we have discussed the electric field is developed for a plate that is denoted as Q by A epsilon naught, and for a particular point at one side it will be in such way. electric field due to this plate will be equal to this one, and it is denoted by E1. Again, if you see the plate here, here is negative charge, and the direction of electric field is just towards the negatively charged. The direction of electric field is always far away from the positive charge and directed to or towards the negative charge. So the electric field for this plate will also be Q by 2 epsilon naught, because the charges on this plate is same in magnitude, but their direction is also same. These electric field lines for these plates and the electric field lines for this plate will also be in same direction. Then total electric field between this region will be is equal to E1 plus E2. Again we have to add, and it will be equal to Q by A epsilon naught. Again, it is sure if we connect the source of EMF and these plates are connected from here. If there is some charges are stored on the plates, this work will be done by this battery or a cell. So work per unit charge that is collected here will be carried out by this EMF. So we can say that charges that is collecting here is directly proportional to the work done by this battery or per unit charge will be denoted as in a form. Again, we know this term as potential difference. Work done upon per unit charge is defined as the potential difference. If we remove the proportionality sign, we have a coefficient here that is denoted by C, and this capacitance is termed out as capacitance. It is a capacitance and it's there like a constant, and it depends upon the shape of our capacitor, it depends upon the area of the plates of a capacitor, and it depends upon the distance between this plate that is due. So we have to find out the formula for the capacitance of a parallel plate capacitor, and this formula will be C is equal to Q by V. As we know that Q by V, and V is equal to the multiple of electric field and distance, that is E into D, and the electric field for this story we have electric field in such a form, and it is Q by A epsilon naught, and it is D. Here Q will be terminated out, and the capacitance of a parallel capacitor is noted as epsilon naught A divided by distance of separation, that is D, and we have the formula of capacitance of a capacitor. Here you are looking this formula, epsilon naught is the permittivity of the medium between the plates, that is this region, and we have epsilon naught if we have free space here. If we put a dielectric here, then this will be K times of capacitance. Here K is the dielectric constant, that is the dielectric constant of that material that is put here. First we have to wipe this, and we will find out more interesting terms related to the capacitance or a capacitor. Just wait. Now I am discussing about the connection of capacitor, and it is in series or it is in parallel combination. We also learned about the combination of resistance in our previous classes, and now the term is for the combination in such a way for the capacitor. Now I am connecting the capacitor, and the three capacitors are connected in series to the source of EMF. Again, if the capacitance is not same for all, and the capacitance of each capacitor is denoted as C1, C2 and C3. For this connection, we know that the path for traveling current is 1. And so our current is I is traveling through the closed circuit. As students, we look here, there is a free space. Here we have a free space, here we have also a free space. So there is a doubt, if we have a free space, how can we see the circuit is closed? If circuit is broken down here and broken down here, how can the current be flow? So it is also a interesting topic, and we will discuss it further. There is also a current, but not in a traditional form as we have previously learned. We have current here also in a free space, that is called displacement current, but we will learn about it in our next classes. So again, I am returning to my topic. If I current is flowing through the closed circuit, so you know I equal to Q by T. Per unit time, Q charge is traveling through this circuit, and on every capacitor there will be charge Q. Q is same for all the capacitors that are connected, because we have common I for this circuit, that is I equal to Q by T. So current will not be divided in series combination, but potential difference is divided in a series combination. If we have potential difference for this capacitor is V1, this is V2 and this is V3, then we have formula for total potential drop is V1 plus V2 plus V3. It is in such a way, and you know Q is equal to CV, then V equal to Q by C. Here Q net by C. Here charges is same for all the capacitor, so it is Q, and capacitance is C1, Q by C2 and Q by C3. Again Q is same for this condition. This Q will be terminated out, and we see here it is equal to 1 by C1 plus 1 by C2 plus 1 by C3. For series combination, we have a reciprocal addition. For series combination, we have the formula 1 by C net equal to 1 by C1, 1 by C2 plus 1 by C3 and such in 1 by C in terms of capacitors. If we connect these capacitors in a parallel combination, just look here, if we connect all these capacitors in parallel combination, then what we will be got to see here, if it is connected to the source of EMF for such type of connection, that is parallel combination. If current I is flowing through the closed circuit and it will be divided in 3 branches, and it is I1, it is I2, it is I3. You know that current is divided in parallel combination, and if I equal to Q divided by T, or for per unit time, if our time is T is equal to 1 second, then it will be also be Q1 by T, Q1 by T, Q2 by T, sorry, and Q3 by T. Here you can see the charges collect on the first capacitor will be Q1, and the charges that will be collected on the second capacitor will be denoted as Q2, and for the last one it is Q3. Then total charge that is carried out by the source of EMF will be equal to Q net, the charges collected by all these capacitors. It is Q1 plus Q2 plus Q3. You know that potential difference is always same for the parallel combination. Here we have potential difference V is same. Then Q net is equal to C net multiplied by V, and it is C1 multiplied by V, C2 multiplied by V, and C3 multiplied by V again. Then if V is same on both sides, V will be terminated. Then for the parallel combination, total capacitance for the parallel combination will be represented as C1 plus C2 plus C3, and it will be going on for the n term, the dot dot plus Cn. So students, I have a question related to the capacitance. First I have to wipe my whiteboard, and I am discussing about this question. So students, I have a capacitor in such a form, and it consists of 3 parallel plates, but it is connected to MF, and middle of the plate is connected to the cell of MFP and creating the potential difference, it is V. And the positive terminal of this cell is connected to adjacent plates in such a way. And we have data for this area that is equal for all these plates, and area of these plates are 200 centimeter square, and separation between adjacent plates is 0.2 millimeter. So we have distance of separation 0.2 millimeter. And the EMF of voltage is that is creating potential difference by the cell is 20 volt. Now we have to find the net charge is available on this plate. So let's see the story. Consider Q charge is available in this plate and it is equally distributed for these plates in form of Q by 2 and Q by 2, just half of the Q charges. As it is connected to the positive terminal of the battery, so here our charge is positive and it is also positively charged. If we have positively charged plates Q by 2 and Q by 2 here, it will a induced charge that will be induced on its surface as negatively charged, and it will be in form of Q by 2 because it is negatively charged, because it is also connected to the negative terminal of the battery. So here we have the charge minus Q and it is equally distributed on both sides of surface as minus Q by 2 minus Q by 2. Again, we have to find the net charge that is Q of this plate. If we are taking it as a capacitor, then we have net charge it is in Q equal to Cv, and here our charge is Q by 2. Again, Q by 2 equal to, and formula of the parallel plate capacitor is epsilon naught A divided by distance of separation multiplied by voltage. If we calculate it and putting the value of permittivity of free space epsilon naught, and it is equal to 8.85 into minus 10 to the power minus 12, and area of this parallel plate is 200 centimeter square, and in the form of meter square it will be 2 into 10 to the power minus 2 meter square. Again, distance of separation is also in 0.2 millimeter, and if we change it into the meters, it will be 0.2 into 10 to the power minus 3 meter, and it will be 0.2 and it will be 2 into 10 to the power minus 4. Again we are making mistake here. If 200 centimeter square will be converted into 2 into 10 to the power minus 4 meter square. Again we putting the value of area to, sorry here, now I am making mistake again here. It is not 2 into 10 to the power minus 4, it will be equal to 200 into 10 to the power minus 4. So our area is 200 into 10 to the power minus 4 meter square. By putting the formula here and the values of area and potential difference in this formula, and our potential difference is V, that is 20 volts, and distance of separation, that is 2 into 10 to the power minus 4. 10 to the power minus 4 and this 10 to the power minus 4 is converted out, and 2 will be terminated by 200 in 100 times. Now we have to calculate it. Q by 2 again it will be calculated as Q by 2 equal to 1.77 into 10 to the power minus 9 coulomb, and charges on these both plates are Q by 2, that is equal to 1.77 into 10 to the power minus 9, and it will be written as nano coulomb. If we have to find the total charge on this plate, that is Q, then it will be Q, that is 2 times of Q by 2. So it will be 2 into 1.77 nano coulomb, that will be equal to 214 and 3.54 nano coulomb. So we have total charge on this plate is equal to 3.54 nano coulomb. So it is our answer, students. I think you understood the concept of capacitor in better way. If you have any doubt, please ask question in our comment section, and I will try to make the concept of physics easy, and make happy yourself with our study channel, and we will learn more and more in our upcoming videos. So let me meet in our next video. Bye bye, students.